Thanks for inviting me. And I think you're all probably familiar with the paper I wrote on this. It was, I think, in December. And I'm just going to talk about sort of um, some of the main ideas that motivated the work, go through some examples, and some more recent work I've done in this direction. So the system I'm going to talk about is called Democritus. You might be familiar with the famous Greek philosopher Democritus, who said he'd rather discover one universal causal law than gain the kingdom of Persia. Um, but it's different from, I would say, the vast majority of work in causal inference, including some of my other work in this area, in the sense that typically in causal inference, you're given data of some kind, for example, a clinical trial, and you're trying to determine if a particular treatment, a drug, is effective in whatever it's trying to accomplish. For example, let's take a COVID vaccine or a medication that treats some underlying condition like blood pressure or so on, something like that. Here, we're trying to infer causality from language. And what I mean by that is um, we're trying to uncover causal mechanisms from documents that describe causal phenomena. So it's a different way of thinking about causality. And so it's important to keep in mind that the kind of structures you construct here are not grounded in data in the way that typical causal inference methods are. So um, what I'm going to talk about is motivated by my work in applying category theory to AGI, which is the class I'm teaching at UMass this spring. I'm not going to assume you know anything about category theory, and in fact, not going to use much category theory in the talk, except it will show up in places when I use sort of categorical language. So in this case, when I talk about a categorical adjoint functor framework, what I mean is functors are like functions in category theory. They're structured mappings that map one category into another. And here the categories we're talking about is language discourse. We can think of language as a category where you have objects like words or sentences, and you have arrows, which are mappings between objects, and those can be viewed as basically putting together words to form sentences or sentences to form documents and so on. And then you have the category of actual quantitative causal models, depending on the formalism you choose. So for example, if you use Perl's structural causal models, one can define a category where every object is a structural causal model, and the arrows are essentially manipulations of the causal model, such as interventions. And so when we talk about adjoint functors here, what I mean is that we're taking language discourse, which is the domain category, and we're converting it into objects in the quantitative causal model category. And it's adjoint in the sense that you can go both ways, in the sense you start with a document which has some causal discourse in it. You convert that into quantitative causal models, and you can go back to the language category by summarizing the quantitative causal models you constructed. So in that sense, I mean, this is a quantitative causal model. I'm sorry, an adjoint functor framework. So so we're typically given some language discourse, like for example, let's say you have a newspaper article that relates to whether eating dark chocolate can help you live longer. This is an example I'll use from the Washington Post. Or for example, whether consuming red wine is good for your health. So there's a well-known paradox called the French paradox, which is that the French have a diet which is involves drinking fairly large quantities of wine as well as eating food that perhaps is not necessarily considered the best kind of food to eat. And they have incredibly lower rates of cardiovascular, illnesses like heart disease than, for example, in the US. So this is called the French paradox because exactly what is going on here in terms of why are the statistics of um, uh, you know the longevity of the French and their health in general so different from the US. So the goal is to construct what's called a left adjoint, which is the mapping from the language discourse into actual quantitative models. And in addition, we're going to be able to rank order them, which is something that was not in the original archive paper, and construct a database, which looks like a standard database using a language like SQL, which is a popular database query language. And there's a reason for doing that, which I'll explain. So the method Democritus builds on some very interesting machine learning methods that came out of category theory. And I'm going to say a little bit about them, but not go into a whole lot of detail. And I'll give you references where you can find all the detail. So the main methods is a kind of backpropagation method that uses diagrams. These are essentially special types of functors that allow you to encode computational objectives. A special kind of transformer model that uses diagrammatic backpropagation. And finally, a way of doing causal inference in a topos. A topos is a kind of category that lets you evaluate causal models locally. So to contrast it with Leopold's work on structural causal models, in a structural causal model, a causal effect is either present or not. It's true or false, which means you're in essentially the world of Boolean logic. In Topos causal models, the logic is intuitionistic. So you can have a causal effect that may hold in one regime, but not in another. And the logic is not binary, it's multi-valued. So there's a NeurIPS paper that I wrote last year that explains the math behind Topos causal models. Excuse me. So let's go through an example. So here's the Washington Post article on whether eating dark chocolate, may help you live longer. And the article refers to a particular kind of alkaloid, theobromine, which is associated with slowing down cellular aging. Now, this is typical of the kind of articles you find in newspapers. In particular, the Washington Post seems to have a habit of essentially putting out a few articles like this every week. And so is the New York Times, for example. And so one can do many things with this. For example, the Washington Post itself has a summary that you can click on, which is essentially running an LLM over the article. And if you do that in this case, you get something like this, which basically says in a few sentences what the article is all about, essentially having to do with a study in aging, finding higher levels of theobromine. And, as is typical for many of these studies, they tend to be associational studies, which is usually what people do. It's often difficult to do true causal studies. And then there are other limitations. For example, it refers to data collected at a single point or a single place and so on. So this is, of course, very useful and widely used in many contexts. If you want a quick summary, it's like the abstract of an article. What Democritus does is quite different. Based on that article, it generates many, many thousands of models that look like this. They're basically like directed graphs where you have snippets of text that serve as variables, which are automatically constructed from the article, and then conjectured causal relations between the articles. So, for example, there's a link between the effects of theobromine on aging and slowing the rate of cellular aging in humans. Um, it also relates to things like, age-related cognitive decline and things like that. Now, this is one of many thousands of models that Democritus can construct. I'm going to explain how it works and then how these models are evaluated. So from the same article, here's a different model that gets constructed, and this looks at a different causal mechanism. This looks at how dark chocolate can regulate blood pressure and things like flavonoids. And so what you end up with is a sort of a rich causal narrative that looks at not one mechanism, but many possible mechanisms and gives you a sort of causal deep dive into the article. And this differs from what a typical large language model will do when it summarizes the article. So how does Democritus work? How does it do it? And what are some of its limitations? I'm going to go through that. So here's another article. This one, again, from the Washington Post about the origins of bipedal walking. So there was a recent study where they discovered fossils from our ancestors almost 7 million years ago. And this study is, again, typical of studies like this. The data is sort of confusing in some ways because you're dealing with fossils collected a long time ago. And there are multiple possible interpretations one can take. So here I'm going to show you how the writer joint works. So in this case, we're going to map back from those graph models I just showed you back to text. And using the internal scoring mechanism, we can sort of come up with what appear to be the most plausible causal explanations and others that seem less plausible. So what Democritus can do is produce some kind of summary of what looks like a credible causal claim, which reads something like this: upright walking causes structural reorganization of the pelvis to support bipedal locomotion. It increases the width and shortening of the pelvis, and so on and so forth. And for example, changes the way the spine is from our ancestors who didn't walk on 2 legs but on 4. Now it can also come up with causal claims that look less credible, and so here's one that was discovered by Democritus as basically saying, Australopithecus afarensis, about the increase in the lower limb bone density during sustained mechanical loading and things like that. So what's interesting here is that all of this is completely automatic in the sense that you just feed in the article and Democritus does its thing and it produces this very rich causal narrative. Of course.
Can I ask a quick question?
Sure, go ahead.
Sorry. Yeah, so are all of these hypotheses that your model proposes from using information from outside of the article, or is it all just based on information in the article?
Yeah, that's a good question. I'm going to go through exactly how it works. And
Okay.
as you can guess, it uses a lot of information that is just not in the article. And that is the strength of Democritus. It queries a large language model for a lot of background information. So the art, if you will, of Democritus is not the information it can get from a large language model, which is just issuing a whole lot of prompts and doing some sort of fairly standard NLP processing. But then once all that data is accumulated, large language models essentially embed all the tokens or words or sentences into Euclidean space, you have to somehow assemble all of that into some coherent causal manifold. And that's where these methods that I mentioned seem to shine. That is, if you just apply standard uh, embedding methods and standard backpropagation or standard transformer, you just get a giant hairball. You just get no structure at all. And so the trick here is how do you pull apart all of these different potential causal structures into something that looks coherent, right? So you'll see how this works. Now, one thing I have to clarify, and I said that at the beginning, these are essentially hypotheses. It doesn't mean that they're to be taken as valid in some sense. They're just plausible explanations. And if you really wanted to do conventional causal inference, you would have to figure out some way of testing each one of these. Of course, in many applications of causal inference, you cannot do classical A/B testing in clinical trials. For example, in this particular case, it would be very hard to do that. In fact, impossible. So what scientists typically do is that they do various other means of trying to come up with a causal explanation. For example, if you're trying to understand why did the dinosaurs die, well, a possible causal explanation is that there was this asteroid that hit in the Gulf of Mexico 65 million years ago and wiped out the dinosaurs. Well, that's a possible causal explanation. But in order for that to have any credibility, you're going to have to find some other evidence that backs it up. So, for example, the presence of iridium in samples all over the world around the time that the asteroid hit suggests that this explanation has some credibility. Okay, here's another example from a PubMed article on the connection between consumption of red wine and cardiovascular health. And once again, Democritus can come up with what it considers to be causal claims that are well supported, and I'll explain exactly how that works, as opposed to causal claims that are not as well supported. So, for example, in this case, it points to things like the French paradox, which, as I mentioned, is a well-known phenomena in this field. It also talks about causal claims that look more speculative. And this has to do with things like enhancing nitric oxide bioavailability. Okay, so let's get to understanding a little bit about how Democritus works. This is from the archive paper. So as you can guess, we don't just look at the article. We, in fact, construct a series of queries to a large language model, and I'll show you all the different models I've tried. And they vary in size from small models, which are, say, 10 billion parameters, to models that are about 250 billion parameters. And there's, of course, dependence on the specific model you use. So you go through a series of steps where you construct some sort of topic graph. You generate potential causal questions from that. You construct causal statements, and you end up with these triples, which are your causal claims. That is, there's some relationship, so there's some subject. So, for example, it could be drinking red wine or something like that. And the relation is some causal relation, for example, increases, reduces, effects, and so on. And then the object is the effect. So the special part of Democritus comes in post-processing. Once you have this data, you have thousands and thousands of these triples. If you just embed these in using a standard sentence embedding transformer, you get no structure at all. You get something that looks just like a Gaussian blob. So the trick is to pull out all the different components. And here we're helped by the fact that we know a lot of information about where this causal triple is coming from. And that, as I'll show, is critical to how the geometric transformer works. And finally, we can sort of reason about the manifold in various ways using Topos theory. And I'm going to illustrate that just by showing you simple things you can do with a database constructed from these causal triples. So the first thing you do, for example, this is the Washington Post article on consumption of dark chocolate and aging, is that from the article, you extract a set of topics, and then you generate what's called a frame of discourse, and this is done by Democritus, where you're trying to find out all the things that could potentially be relevant in this article or to this article. So, that could be general things like association versus causation in aging studies. It could be things like, cancer risk reduction strategies, the ingredients in dark chocolate, something about DNA, advice of physicians, and then, of course, what the article talked about, which is theobromine. And all of this is done without having necessarily any input from the user, except a sort of a compute budget, because as I'll show you, it can be expensive to compute this. And so one of the parameters you can set is essentially how large of a frame of discourse do you want to construct. And usually if you construct, in this case, for example, a dozen or 2 dozen topics, that seems to provide a fairly rich set of causal models that get constructed. So in order for this to make sense, Democritus sort of uses a set of principles, and there are sort of very obvious principles, which is these statements that are constructed are considered hypotheses, and they're not causal ground truth because, of course, you can't establish that in most of these problems. And in special cases, when you can do A/B testing, you'd have to actually go and do field work to establish ground truth. So the goal of Democritus is not conventional causal inference like clinical trial. It is to generate this causal narrative. And one reason it works, which is in a way surprising, is because it turns out that it works in a way that's sort of like many machine learning methods that work with data that or hypotheses that by themselves are not very reliable, but by statistical averaging, you get a lot of reliability, just like, for example, bagging or boosting methods. Here, because you can generate tens of thousands of these things, and you're checking and cross-checking, if you have individual causal claims that are just completely crazy, because an LLM has been trained on vast quantities of data over the web, it's bound to have sort of included within it things that are just highly speculative, but they fall by the wayside because they're not supported by anything else. So you might have some crazy causal claim out there, which is the LLM has been trained on, but it's not supported by lots of other things. So in a sense, Democritus constructs a causal narrative that reflects, in a way, what society believes about this phenomenon, which of course includes a lot of the scientific literature. And all of the data is stored, and you can check, the provenance of any of these. So there's no real mystery to where something comes from. And then when you construct this right adjoint, which goes back from the causal models to the causal narrative, you can suppress things that just don't seem to have a lot of support from multiple sources. So these are basically the way things work that makes Democritus actually quite useful in many of the examples that I've tried. Okay, so just to give you a sense of how quickly it runs, this is roughly the time in the beginning. Actually, it took much longer. And then we came up with some computational tricks to speed up the processing. And as you can see from here, the bulk of the time is spent in the questions and the processing that involves LLMs. So as you've probably read in lots of accounts, the inference time of LLMs is their sort of biggest Achilles heel, in the sense that it's very expensive to run these 100 billion parameter models, and you're running them repeatedly over and over again. So you can do some tricks, but at the end of the day, that's going to dominate your costs. And actually, the machine learning part of it is relatively trivial in terms of the compute costs. So it takes about 5 to 6 minutes to do a single document, which is obviously not real time. But on the other hand, the goal of Democritus is not real time, but to give you a sort of a deep dive into a document or a collection of documents. Okay, so the kinds of LLMs you can use are obviously there are potentially hundreds of LLMs you could use. One of the ones I've used is, of course, from OpenAI, where it's hosted by them, so you have to use an API interface. And not surprisingly, this gives you very high quality, but then you pay for the latency because you're doing all these network access calls, and that's going to slow down the processing. I've also run quite a few locally hosted LLMs on my Mac Studios, which are again fairly expensive because they come with a lot of RAM. And I can run up to a 200 billion parameter model, and depends again on the model. So in the Qwen 3 case, which is about 80 billion parameters, it tends to work less well than the OpenAI model. My guess is that the Qwen model has not been tuned quite as well to be on topic. And so you end up with these drifts where it goes off into some tangential topic that has nothing to do with the main document that you gave it as input. The larger models are, as you'd expect, better. They've been trained on more data. But it turns out even the GPT models can be actually less reliable if you use their open source variants. So the GPT OSS is their open source version, which tends to be actually quite a bit worse than the API version. And that's not surprising. I suspect the best models that they have, they preserve for their own use in terms of charging you for it. But even if you look at the API costs, it's really fairly minimal as long as you're willing to put up with the network delay. This is from the point of view of the cost, it's actually fairly minor. So it's not like if you've been reading what's happening in the AGI world now, OpenClaw is the latest rage about this autonomous agents that can go off and do things for you. And these can generate millions and millions of token requests. And they're being, people who've been using them have been shut down by, their accounts have been closed by OpenAI and Google and Anthropic because they can generate enormous number of token requests. And here we're not in that kind of territory. Okay, so let's get a little bit deeper into how Democritus works. So obviously, LLMs are a big part of, getting the background to any article and doing topic discovery and elaboration. But then there are these other pieces that are necessary once you get the raw data. The raw data is these triples that you get, which are the plausible causal phenomena, but you still have to assemble all of those into some coherent manifold structure. So critical is this extension of backpropagation that I call diagrammatic backpropagation. I'll say a little bit about how it works. It constructs diagrams, which are essentially constraints. For example, compositional constraints or commutative constraints, and then constructs a loss function from those constraints, which is added on to the traditional backpropagation. And the geometric transformer takes this traditional transformer, which uses self-attention, which is essentially dot product over all tokens or pairs of tokens. and then lifts the token space to you can think of it as a graph space, but it's actually a simplicial space where it can introduce these constraints again. It's sort of like an inductive bias. So it benefits from the fact that for these causal triples, you know something about the topic or the domain, and so you can keep things separate even if they end up in the same embedding space. And the last part is the use of fairly esoteric tools from Topos theory, which is a type of category that has an internal intuitionistic logical language. And the development of Topos theory in pure math over the last, I would say, 60 years has been one of the sort of major achievements of pure mathematics in the 20th century. And we're slowly discovering all the, the cool things that we can do with it. And Democritus is why it's one of the first to use a lot of Topos theory in its processing. So for part of the course I'm teaching, I wrote a kind of textbook for the course, which gets into a lot of the math behind this. So if you're interested, it's freely downloadable from my webpage. It's called Categories for AGI. It's about 300 pages and gives you a lot of the background math that you need if you really want to dig into how these things work. Okay, so I'm going to go through a few more examples and I'll illustrate other aspects of the system. So in the original article on arXiv, I used this because my father spent a good deal of his life actually studying this ancient civilization. It's called the Indus civilization that prospered, 2500 BC or so. And suddenly they died off, and it was not clear exactly what happened because it was a flourishing civilization. And this history doesn't record any wars during that time. It looks like the most plausible explanation is actually climate change. There was a series of droughts, and they were living as most ancient civilizations along a huge river called the Indus River, which is now between India and Pakistan. Of course, there was no India or no Pakistan in 2500 BC. And the Harappan civilization used the river just like the Egyptian civilization did for all their commerce. So the fact that there was a significant drought for several decades meant their main source of commerce was, badly affected. And so this is an article that appeared in Nature, constructing very detailed causal explanation for what happened. And based on this article, you can use Democritus to expand out the causal narrative and build something that looks like a global causal manifold. This is a 2D illustration using UMAP, which is a very popular data visualization method. And you can see that the narrative includes things like trade between the Indus civilization, Mesopotamia, and Egypt, and including trade with the Romans. It includes things like irrigation. It includes sort of, the monsoon, which is a major part of the weather patterns in South Asia, and farming practices, and things like climate-induced crop shifts, and so on. So illustrates that typically in these kinds of studies, you have to bring to bear a vast amount of knowledge from many different sources. And this is the kind of thing that's tailor-made for Democritus because it has the benefit of using one of these really powerful large language models that just knows an amazing amount about lots of things, and it can bring together all of this information. So another thing you can do is to basically generate causal claims across many, many domains. So this is a data set about 100,000 causal claims across economics, education, the law, marketing, medicine, engineering, public health, and so on. And then you want to assemble all of these into some sort of coherent structure, and this is done just primarily to illustrate uh, the advantages of this geometric transformer. If you just took all of these, and this is, for example, just the claims from economics, and you just showed the raw sentence embeddings from running a sentence transformer on it, you get essentially what looks like a giant hairball with no structure at all, because everything piles up on top of everything else. But then if you do the post-processing using the geometric transformer with diagrammatic backpropagation, you get something that looks much nicer. All of the different pieces pull apart, and you see a lot of structure that separates out, for example, causal claims in law with from medicine, engineering, marketing, and so on. So this is really in some sense, the secret sauce behind how Democritus works is the ability to essentially construct these embeddings by taking advantage of the fact that you have these higher level labels that tell you all of these different uh, topics and the hierarchy that you get. So, for example, it's not just that you know that a causal claim comes from economics or law or medicine, but you also know which area in the law or which area in economics or which area in medicine and so on. So you have this hierarchical labeling structure, which then can be input as kind of an inductive bias to the geometric transformer, and diagrammatic backpropagation will then respect that structure. You can think of this like a causal grammar, if you will. And so you're processing the data not just in terms of the data, the raw embeddings, but being influenced by this grammar as well. So very briefly, this is how it works. You have these diagrams in category theory, which look like this. So here the circles denote objects. So for example, A, B, and C are objects, and then the arrows are denoted by the edges. So we have an arrow from A to B that is marked F. In a typical use of these diagrams in category theory, for example, A, B, and C could be fairly complicated things. For example, they could be topological spaces, and then the arrows F, G, and H are continuous functions. There could be measurable spaces, in which case these are measure-preserving functions. In our setting, they could be, for example, transformer models, and you're composing transformer models. So in this diagram on the left, you might impose a constraint that the composition of F and G must be equal to H. And so this can be treated as a constraint that is enforced. In the one on the right, you have a commutative diagram which says there are two ways of getting from object U to W. You can go through X or you can go through V. And these are typically used in category theory to express a very large number of different properties. So in a sense, category theory is like a unified field theory of math in the sense that it largely consists of analyzing diagrammatic structures like this, and then proving theorems about just these abstract diagrams. So it was originally called abstract nonsense by the mathematicians who developed it. And that term was pretty much stuck because in a way that describes it really well. And it turns out very interestingly, like these abstract diagrams encode an amazing amount of math that unifies many, many different fields in math. So for example, Topos theory unifies a vast array of mathematics, from geometry to analysis to logic. And you see that there is sort of this unity among all these different fields in math that you would never have discovered. Just like modern day physics, for example, uses bosons and fermions and abstractions like that to unify all the different forces that were considered earlier to be separate. So based on this diagrammatic structure, I had sort of conjectured a couple of years ago about how to build generative AI, and it was a theoretical paper. So Democritus is in some sense one of the first implementations of this theoretical vision that I sort of laid out 2 years ago. It doesn't capture the full richness of what I proposed, but one of our goals is to see how far we can get with, within a reasonable compute budget. So you don't have to get into the details of this, but essentially at a high level, there's this idea of curvature, which is trying to measure the loss of these constraints. So if you think of each of these triangle constraints and rectangle constraints as constructing or yielding an error function, you can coerce backpropagation to minimize these error functions in addition to the standard mean square loss or cross entropy loss that is typically done in backpropagation. And there are other things that I'm not showing that you can enforce, for example, things like lifting diagrams, which is used to model database inference. Okay, so the geometric transformer, as I mentioned earlier, takes a standard transformer. And a standard transformer, you start with essentially a long sequence of tokens, and then you construct basically a dot product structure. You're just comparing pairs of tokens. It's kind of like a correlation score. And then you end up with this attention matrix, which is just processed in a number of ways by doing layer normalization and the standard multi-layer feed-forward network. What the geometric transformer does is it takes these tokens and lifts them into a geometry or a graph space where it enforces these diagrammatic constraints. And I don't want to get into the details of how this works, but there is a way of abstracting out the construction that you typically do in deep learning into this more abstract geometry space. You have things like horns, which are like, gaps in your graph structure that you can fill. And based on this kind of architecture, which Democritus can actually tease apart all of these causal triples that would otherwise overlap in the same space. Okay, so I'll finish up by just giving you the last part about this, which is the use of Topos theory to do causal inference. One of the reasons you need this is because you end up with a vast number of causal models, and then you have to have some way of combining them. And if you think about running something like Democritus on a large collection of papers from PubMed has millions of papers. So even if you take one particular area, like, the effect of red wine on health, there are probably thousands or tens of thousands of studies. And you want to somehow combine all of that. And so you will end up with a vast amount of data that you have to somehow sort through. And so we use Topos theory, and now Topos theory can be used in conventional causal inference. So if you look at my paper in Europe's on Topos causal models, that's basically classical causal inference. I showed that Pearl's structural causal models is a special case of a Topos causal model, and that you can generalize Pearl's work. So you can take his do calculus rules and you can construct a more general version for Topos causal models that uses intuitionistic logic. A Topos is a category that looks like a category of sets, in the sets you can take two sets and form the union or intersection. This is abstracted in Topos theory into things called limits and co-limits. You can take a set and construct a subset. In Topos theory, this is a sub-object classifier. And then in classical set theory, you have Boolean logic, which is a way of describing set theory. In a Topos, you end up with something that is not Boolean. It's multi-valued. It's an intuitionistic logic that has a special kind of internal logic called the Michel-Benabou logic, which has a possible worlds semantic interpretation, which is often referred to as the Kripke-Joel interpretation. So if you're familiar with the work of philosopher Saul Kripke on possible world semantics, that plays a key role in Topos theory. So one reason we need this is, of course, we get thousands and thousands of these documents, these causal models, and they're scored in various ways. I won't get into the details of what the scoring is, but it's essentially a reflection of um, the internal coherence of a model as compared to all the other models you're also constructing. So model is considered more plausible if it is supported by many, many similar models. So you can think of this as sort of traversing paths in the causal landscape that are well traversed by other models, and you gain support statistically in this way. There's a detailed way of constructing these scoring functions, which again, I don't want to get into. They're not terribly important. But there's a way of sort of measuring the internal, complexity of each of these causal models. Okay, so one way to motivate this is what if you had multiple studies? So here's a simple example where we have two PubMed articles that both relate to the effect of red wine on your health. And they approach it from different perspectives. What are the critical ingredients in red wine, which comes from the skin of the grapes, is resveratrol, which is a well-known antioxidant. And so these articles take different points of view on this. And so one way we deal with this is we take the causal structures and we compile them into a database. And there's a archive paper on this, which basically tells you the language of this. It looks like a standard database, except it's intended primarily to do causal inference. And you can compare this to other ways that LLMs have been supplemented. For example, there is well-known things like RAG, which is retrieval augmented generation, and knowledge graphs, which coerces an LLM to follow some established predefined ontology. And this is now part of the industry practice in using LLMs. And CSQL, which is this causal SQL, is different in the sense that it is primarily designated to do causal inference as opposed to knowledge graphs, which are all about semantic ontologies. So we can do causal inference by just sort of, as I mentioned, things like, looking at which edges seem the most well supported by the maximum number of models. And so we can find out the influencers in the space by looking at nodes that have a very large outgoing score, nodes that have a lot of influence. And then we can sort of toss out causal claims that seem fragile by using these internal scores. This is, again, a little bit of category theory to show you that there are ways of taking multiple causal claims from documents and constructing their pullback. So here, think of F and G as mappings that go from causal document sources. Like, for example, A and B could be two studies, and F and G map each study into the category of causal claims. And then P is sort of a pullback, which says, what are the causal claims in documents A and B that basically both map onto the same object in C? And there's a lot of interesting properties about things like pullbacks. And we can use that to do this. And we have to do some sort of soft pullback because we can't get exact matches because we're dealing with text. But when you do this, you end up with interesting things like, for example, you can discover things that the articles agree on. For example, that one of the causal mechanisms by which red wine is beneficial is that resveratrol seems to affect mitochondrial biogenesis, which is a measure of how much energy is produced by your cells. And you can sort of score each of these things that show up in these documents. And you can discover other things that they agree on. For example, the endothelium is the internal organ that is important for blood flow in your body. And resveratrol, again, seems to improve the functioning of your endothelium. And this is another way that red wine is conjectured to have a beneficial effect. Okay, I can go to some other examples, but you get the idea that you can apply this across the board to various studies that show up both in popular press and in the technical medical literature, and you try to combine each one of these. And we're just at the beginning of understanding how to use this technology. And so there's a lot of potential applications that you could imagine. And of course, one has to do a fairly rigorous analysis of how much you can trust what's coming out of all this. And this again will depend on the expertise of people who work in specific domains, whether it's medicine, like in this example, or economics, or for example, archaeologists, or you know, people in engineering or public health and so on. Okay, you can do other things like push outs, which I won't get into, but this is another way of sort of trying to find out combined support between multiple documents, multiple claims. Um, Let me end with the last example, which is this idea of sub-object classifier. So one of the things that distinguishes Topos theory is that the logic is not Boolean, but it's multi-valued. So one way to understand this in this example is you may have causal claims that are supported by one study A only or the other study B only, supported by both of them in a strong way or supported by both of them in some weak way. And this is a simple example of how the logic is multi-valued in the sense that this becomes the object of truth. So a statement is causally not true or false, but it takes on one of these many values. And in my paper on Topos causal models in last year's NeurIPS, I go through this. And there's a much longer archive paper that I wrote on intuitionistic do calculus using Topos theory, where I formalize a lot of this. So you can look at that article. So let me end there. You can find out a lot of background and all the things I talked about by looking at the papers. I think you're all familiar with the first paper, which is the original Democritus paper. The NeurIPS paper basically just focuses on conventional causal inference, but explains the Topos theory part of it. And then there were two follow-on papers that I did showing one was a more theoretical paper on generalizing Euler-Pearl's do calculus to the intuitionistic setting. And the other was an experimental paper showing how you can get practical causal discovery methods from this. I call this judo calculus because there's a type of topology that you impose in a topos. And in the NeurIPS paper, this was based on the work of the mathematician Grothendieck, so it's called Grothendieck topology. In the archive paper, I generalized this to a different kind of topology, which is based on this operator J, which maps a subobject to another subobject, and that's why I call it J-do calculus. It became judo calculus. There's a paper on CSQL, and all of this is sort of written out in kind of a textbook form, along with some other things which I'm using right now for my course. There's a GitHub repo where you can run sample code for a lot of this. Some of the code involves a fairly, heavy duty processing by GPU machines, so it's not on the repository. Eventually, I'll end up putting most of it there. So in summary, Democritus is a system that essentially constructs causal models from causal language discourse. It's different from traditional causal inference in that its input and output is text, as opposed to traditional causal inference, which usually takes a numerical data and converts it into mathematical causal models. And it can construct many causal models and rank order them. And you can also store them in a database so that you can do various interesting processing after you construct the models. It's critical to use LLMs for this because you need, this knowledge base that allows you to construct all the background information to understand what the original document is all about. And it relies on this key categorical machine learning methods for its work. This is still ongoing research, so there's a lot we don't understand about how this works. In fact, in teaching the class yesterday, we discovered some potential quirks with the way the geometric transformer works, and that's inspired some more research into this. So I'm sure with the help of the students in the class, I'll discover more interesting things about this. And there are other people starting to use some of this as well. Okay, so let me stop there. Thank you.
Yeah, thank you very much. Very interesting. Questions, anybody?
I can start with one. My guess is that from what you explained, there a lot of the reasoning come from the LLM itself. So the quality of the LLM and the training that the LLM being used or trained on the dataset is determine the causality models. How do you can compare between the two?
Yeah, that's a good question.
Models.
So you're right. So the LLM is kind of providing you the raw data, if you will, right? Because it's basically generating all these causal claims from its data, from its internal knowledge stored as weights. And of course, if you use say a small model like an 8 billion parameter model that's being distilled as opposed to like a 200 or a 500 billion parameter model, the results will be quite different. And so a lot of this will depend on a potential use case. So it might be that for some specific domain, you can get away with using a small model. But if you want to build a general purpose Democritus, invariably you're going to have to use one of these larger models. Another possibility is that how much variability is there if you run this, say, for example, repeatedly. It turns out most of the processing is fairly deterministic. So there's not a lot of statistical variability once you fix, of course, the LLM you're using and the documents you're starting with. A lot of the variability, of course, is the LLM itself, which is exactly what you're asking about. And, so you might imagine if you had a ridiculous amount of compute budget, is to build a customized LLM that can basically just provide you with exactly what you need. So you could distill out, sort of a causal Democritus LLM, but that requires doing a lot of distillation, and I think you run into problems either with compute budget or with constraints on how many tokens you can query LLMs with. This is exactly the controversy that has happened recently. I don't know if you've heard this, but the major LLM vendors in the Bay Area, which is Anthropic and OpenAI, and in fact, I think Google as well, have accused Chinese companies of essentially generating tens of thousands of kind of fake accounts in a way, if you will, to just generate vast amounts of interaction data, which they then use to post-process and train their internal models better. And it's not surprising to me this is happening, of course, because it's exactly what you'd expect in a very competitive landscape. And so a lot of this variability comes from how well the LLM has been tuned. So LLMs, in a sense, they're like in a strange way, they're sort of like our internal mental models. We tend to free associate between topics, and LLMs will do that. So they tend to be not very constrained by the original query you ask them, unless you impose on them, some strict constraints. So in some sense, the better tuned LLMs tend to be more faithful to the original question you asked, and the the weaker ones tend to drift off into tangential topics that have nothing to do at all with the causal system.
Right. The reason I'm asking that is because part of the things that we consider to do is to use this kind of models to extract causality from biology data, ion channels, interventions and stuff like that. And I'm asking what kind of LLM do I need to do, because it doesn't seem for me that the LLM that been used to, I don't know, learn on Shakespeare can do the same thing on ion channels.
Yeah, that's right. That's right. So again, I think this is a question that you'd have to explore yourself, in the sense that it could be that if you are interested in using Democritus for your application, as opposed to, say, something in causality and law, or like I'll just mention, for example, Joe Halpern is a well-known AI researcher who recently died. And he's well known for many things, but one is his work on what's called actual causality with their Pearl. Actual causality refers to causality and the law, which is, in actual causality, you're not trying to find some general causal phenomenon. You're trying to understand very, very specific things like, why did this particular crime happen? And who did, for example, who murdered someone? And that's an example of actual causality. You're trying to narrow down a causal claim to one particular individual. And so I suspect that depending on the end use, it might be that you need a particular kind of LLM. Or, like I said, if you have a vast compute budget, you could train your own, although that tends to be very expensive. So these are all questions for which I don't think we have good answers yet, but that's part of the research, is to figure out, how to use these. And I know in the Bay Area, there's a lot of people using LLMs for making causal discoveries in biology and other domains. So I think that's part of the goal here. One thing that I'm pretty sure of is that you can't just use an LLM, no matter which one you use, to get the kinds of structures that Democritus produces, because you end up with many possible things that have to be somehow reconciled. And you need something like a geometric transformer to tease apart, all of these different structures. So that part of it seems, at least so far, it looks like it's something that's necessary. You might be able to use one of the, geometric, or excuse me, one of these graph-based or hyperedge transformer models that might have, similar capabilities. I haven't explored those yet. But you need something beyond sort of vanilla backpropagation and vanilla transformer models, I think, in order to put together lots of these different pieces of information into something that looks coherent.
Thank you.
Anyone else? Santosh, go for it.
Yeah, so one of the things LLMs are notorious for is sycophancy, right? So you make an outlandish claim, and you can get an LLM to justify it using even like coherent, plausible sounding arguments. I know there are ways to deal with it, but does your method have to deal with it in some way? So if you completely fabricate the paper and make a claim like, people have the most vivid dreams in places where it rains a lot or something like that, and write an entire paper, and you run your method, can it still find, just sort of curiosity, can it still find like plausible sounding causal model for that and give it a good score?
Yeah, that's a good question. I haven't tried. That sounds like a really fun example to try. I thought of doing something like that. I think the reason you'll end up in difficulty there is you could start with some, piece of fiction, let's say. I mean, you could try to perfect short story like that, right? It should be fine because it's obviously fiction. But if you started with that as your original causal document, The problem is that you wouldn't find many sources of information that backs it up. So yes, you could draw causal links between things that look completely spurious, like rain and dreams or something. But then in the background literature, there just would not be support for that. Right. So essentially what would happen is Democritus would come back with lots of possible things, but all of them would have very weak scores, that it just wouldn't find convincing evidence that is supported by the literature. So Democritus, in some sense, relies on the literature to the extent that that literature has been incorporated into the LLM. And so I think to get back to the earlier question, that's why the choice of the LLM is important. You could obviously fool Democritus by using an LLM that's trained purely on, say, fiction, for example, right? In which case it has no ground truth causal information to back up anything, right? But these models that I'm using are not like that. They've basically been trained on pretty much everything. And so when you actually query them, you get back lots and lots of scientifically plausible causal claims, because that reflects the data that they've been trained on, right? They've been trained on basically pretty much the entire PubMed database and the entire archive database and so on. So all of that's already built in there. And that's essentially why this works at all. If it was trained purely on fiction, I agree with you. I mean, you would end up, sort of hallucinating a lot. That's not to say hallucinations are impossible. I think anytime you deal with LLMs, you just can't avoid that. But I think you can minimize that by essentially not believing something unless you see that being supported by a lot of, other evidence. And that, I think that's why it works, to the extent it works, yeah.
But what if a long causal chain has like many links, but each of those links are supported? For example, a link between rain and heat, and then a separate link between heat and, say, neurons firing, and then neurons firing in dreams or something like that. So if you put all of those individual things together, then you would get a coherent story, right?
Sure. You could get individual causal paths, each of which has strong support, but the composition of them does not. And that's entirely possible. But again, the way Democritus scoring works is it's not just looking at each individual link. It's actually looking at how much support the overall causal path is getting in terms of how many other causal narratives are traversing the same path. And there is where long chains that are speculative will get dropped out, because they're just not part of a large number of other explanations, right? And I think the strength here is that we rely on the fact that things that look credible are things that just keep showing up over and over again in different studies. And I think that's why this tends to work.
That makes sense. Okay, cool. Thank you.
Just a quick question. I always wonder, when we make these, articles and newspapers, obviously, but also papers in human language, I wonder how much we're missing, and in the sense of making it difficult for these kinds of things. Do you think anything would be better if we were to release some sort of markdown version of these kinds of studies that were better suitable, or conversely, do you think would actually be worse if they weren't cashed out in human language?
Yeah, that's a good question. I mean, I always thought about, are there ways of actually getting at ground truth? Because a lot of these studies, you don't have access to, for example, the lab data necessarily. Sometimes you do. I know some papers require you to sort of, there's usually a method section, and these days increasingly papers come with data sets. So one of the extensions that we've been considering with this is to actually hook it up to actual lab data in the cases where you have access to that. So I know people have tried this, and there are other papers. There's a growing literature on the use of LLMs for causal inference. where they're trying to do, typical causal inference, but use the LLM as a way of filtering out, you know, plausible causal hypotheses. The problem with causal inference is that even if you restrict yourself to DAG models, the number of possible DAG models is super exponential, the number of causal variables. So even if you take something really small, like 10 or 20 variables, you can end up with hundreds of millions of possible DAG models, and it's an enormous space to search. So the methods that are there sort of work by essentially trying to figure out ways of constraining this space in some way. But they all have a problem in scaling, which is, I think, one of the reasons why causal inference has never, I would say, in the last 30 years or so, produced something that scales to sort of web level, as opposed to LLMs, which, given all their limitations, one of the strengths is that they can basically be run on trillions of tokens and the entire corpus of human data, in fact. Whereas you just couldn't run any causal discovery algorithm on the entire, if you take all the experiments ever done in medicine or something, and you try to do causal discovery, you would just end up with, you run into huge problems. And so you can think of Democritus as some sort of, halfway house here, where you give up some of the benefits of actually working with real data, but then you get the advantages of working with LLMs. But I think it would be very interesting to actually provide a backend to this, which hooks this into real data, maybe even in an interactive setting, so that you have ways of actually confirming the validity of any particular claim that's made. And that, of course, requires the ability to be able to do experiments. One can try to do that with, in sort of a simulation world. So you can imagine trying to do this in some sort of simulated biology world or simulated economics world, where you can actually run A/B tests or other things to check for plausibility.